Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to discussion on pre-processing of spatial data sets. Earlier we also touched upon this and some processing or pre-processing of spatial data sets we have discussed in part 1. So now we will have in part 2 and also one more part is there, part 3, which we will discuss after this discussion. As you know that format conversion, data reduction generalization, error detection, this we have all discussed. Now in this discussion I would like to have on merging. Merging has got little different meanings but in order to separate it, one is edge matching and that is the adjacent data sets are merged or matched, whereas merging can be also merging two different data sets belonging to the same geographic system and then creating a new product, that is also merging. Some people also use word in digital image processing domain and they use the word this edge enhancement, not really exactly edge enhancement but image fusion. They also use image fusion or sharpen, image sharpen. So there are different terminologies are there because as you know in GIS lot of tools or techniques which were there in other domains have been incorporated or are being incorporated, therefore sometimes little different terminologies are there. So merging means merging two different data sets belonging to the same area, same geographic coverage. Also this pan sharpening, they say also PAN for panchromatic, using panchromatic data, pan sharpening, and also image fusion. So all these will come under this category. So let's start with that. And that here what we do basically, this is a typical discussion related with digital image processing, but in GIS we also keep doing all this. So that is why it is important to discuss here also. And because major input in our GIS nowadays as data is coming from satellite data, and therefore as we know that there are various satellites having various sensors and many of such data sets are freely available, and therefore user try to use them as innovatively, as judiciously for different kind of projects. So in this discussion I will be showing some real examples which I have used in different projects or different research or studies to bring out some very relevant information. So multi-sensor image fusion is the process of combining basically relevant information of the same area from two or more images into a single image. Now when we say two or more images, there may be a scanned map also, and that map we can treat as an image and can merge with the other data sets. So it has got different meanings here, but the main purpose is that two different data sets belonging to the same area are merged or fused or pan sharpened. And whatever we do in this image merging or fusion, and the result can be more informative than the input image, individual input image, and you would see in the examples also how they become beneficial. So if two different resolution images are with you of the same area, say belonging to the almost same time, they may not be that useful individually, but if I merge them or fuse them, I may take lot of advantages of that. Means taking advantage of one thing from one image, another advantage of another image and then fusing it and creating more things. And as I have already said that lot of data is becoming available, and a lot of data is also available on net free of cost. So, we can try all these combinations. Now, in many applications sometimes we require both high spectral and high spatial resolution. High spectral means here, those who may not be familiar with remote sensing, high spectral means that for a same part of electromagnetic band there are more narrow bands are available and more number of bands are available, and therefore we say high spectral. Suppose there might be in earlier sensor systems there might be a band having 0.1 micrometer difference. Now we are having 0.05 micrometer difference. So, more narrow bands are available, more number of bands are available for the same part of EM spectrum, and therefore we call as a high spectral resolution. So, image fusion basically allows us to integrate different information sources. I have also said that image with map after scanning can also become a raster image, and that can be merged. And these images, these fused or merged images can have complementary spatial and spectral characteristics. And as you know, in the satellite based remote sensing or satellite imaging, two types of images are available. Panchromatic, which has become quite common with high spatial resolution, and the multispectral images with relatively coarser resolution. So, one is a panchromatic, that means black and white image, but having high spatial resolution. Another one is having relatively coarser resolution, but having multispectral images, that means the colored images I can create. So, by exploiting this image fusion or image merging technique, I can exploit the both best of these two, panchromatic as well as multispectral images. So, I can exploit the high spatial resolution of panchromatic images, and I can exploit the multispectral or colored different bands of relatively coarser resolution images, and can create a new product. As you know that for pen sharpen, when we say pen sharpen, so pen stands here, PAN stands for panchromatic. So, these panchromatic images are generally merged with multispectral data to bring more information out of that or convey better information. Before that, just little fundamental I have to discuss this. This color space or color cube is known to us since our high school, CBSE high school or so. As you know that there are 8 corners in this one, this in color space. Color space can be represented using different models. I am using this cube model, color cube model. So, on one corner you are having of this cube, I am having the red color, and then on another diagonally opposite corner I am having blue color, and again diagonally opposite to these blue and red I am having green color. So, that means using this color space I can create a plane which can touch all these 3 primary colors, that is red, green and blue. But at the same time these are called additive color schemes, and at the same time I can also use a different plane which will start say cyan color. Then I am having diagonally opposite color is the magenta color at this corner, cyan is this corner, and then finally I am having yellow color. So, this scheme is called subtractive color scheme. This scheme we have discussed in earlier discussion, that is this scheme is followed by the printing devices, but for our computer screen or projection systems we use the primary color schemes. Now, after completing 6 colors, that is red, green and blue, magenta, cyan and green, and now we left with magenta, cyan, yellow. Now we left with 2 more ends of these or corners of this color cube. One is the white and another one is the black, which is at the far end, at the far end of this color cube. So that makes our complete color space. Now I can create a plane which will touch red, green, blue. I can create a plane which can touch cyan, magenta, yellow, and black and white can become my intensity. So using this concept, I can play with the colors within our data or within our images, and exploiting this I can also create merged or fused image. So this is how it is important. Now I can also take out a cube, a cone out of this cube, which you can see here. So that on the periphery it becomes the hue or colors. So as I rotate around this, I keep changing the colors, or from center of or from base of this cube or center of this cone axis, if I go away from that, then I am going towards more saturation. So this becomes my saturation, and then I am having also brightness or intensity starting from 0, which is the base of the cone or apex of the cone, and base is here, which is white. So that means out of this color cube which is shown here on the left side, I can take out a color cone as well to understand these things in a much easier manner. Now instead of 3D, I can now also represent in 2D in more simplified manner, that I am having on this hue periphery, I can have red and green and blue. RGB is here, cyan, magenta and yellow are here. And of course, if I go downward, then this is my intensity scale, and of course this is black and this is white. And if I come out from the center of this base of the cone to away from that, that becomes my saturation. So here the saturation. So I can use these equations to achieve all this by playing within this color cube. So now what example I am going to show you, in which I am using a pen image, or you can call as a pen sharpening or a pen image merging, image fusion technique. So I am having a pen image which is having high spatial resolution 5.8 meter, and I am having list 3 FCC image which is having 23.5 meter resolution. So list 3 image is having, but this is a false color composite, that means it is representing a multispectral image, but relatively it is having coarser resolution. So what resolution it is having? About 23.5 meter, and this one pen is having 5.8 meter. But here this is a pen image, so single band I am having just one band here, and here I am having, when it is FCC, so I am having 3 bands here. So using these two qualities of two different images belonging to the same area, the first step is to do the image to image registration. Recall the georeferencing. That means I am asking here the georeferencing. So after doing this georeferencing, I can now play with that color space, and what we can do, that since this is RGB or red green blue image, this is red green blue image, this one. So what I will do, I will split into IHS, because that I can play in color space. Instead of projecting my image into RGB plane within color space, I can project into IHS, that is intensity, hue and saturation. So here that image which was colored image for FCC RGB image has been splitted into 3 components: intensity, hue and saturation. So this intensity image is dropped here, whereas a hue image and saturation image continues for our use, and intensity image, our pen image, which is having high spatial resolution, becomes our intensity image. So this becomes our intensity image, and these two hue and saturation image. Then we can go for backward transformation, that is from IHS to RGB. So first we split it into RGB to IHS. I was replaced with the pen image, hue and saturation image continued, and then later on from we did the backward transformation from IHS to RGB. And then we can achieve a merge image which will have the best qualities of both pen and FCC image or colored image or multispectral image, and by which we can create a very unique product, very useful product, which will bear the best qualities of these two input data sets. In isolation, independently, these two data sets may not be very useful, but if I combine, I can be the output image can be very useful. Now there are certain constraints are there, and the first one is that the date of these two scenes should be as near as possible, or if it is same, that is very good, like in our example. But if it is not same, because the season, if the season changes or year changes, maybe having the same date or same time, but if year changes, then you may get the differences, and that would be unnecessary information or artifacts. So we do not want, therefore one should try to get the same date image, and it is not difficult nowadays because lot of data is available and that can be exploited. Now this is our input pen image, which you can see here, and then this is our list 3 image, which is of course a false color composite or colored image. This is having a 23.5 meter resolution, and this is having 5.8 meter resolution. So by showing this flow chart or methodology, we can merge these two images into a new product. Now this product is bearing high spatial resolution as well as colors. At this zoom level, you may not see the efficacies or advantages of merge images. So let me bring a more zoomed part of this image, which is a Delhi golf course. As you can see in the FCC image, which is having 23.5 meter resolution, the individual holes of a golf course cannot be seen very easily in this image. Whereas if you see in pen image, though it is black and white image, but it is having high spatial resolution, that is 5.8 meter, and therefore these different holes of this golf course are very much visible. And when we go for this merge image, as you can see that now this image has become colored, as well as all those golf holes which were not visible in FCC image are also available here. So the spatial resolution has come from pen image, and spectral resolution has come from MSS or list 3 image, and then we get a new product. So this is how we can take advantage of this. Now once you become comfortable with such merging techniques, you can play further with these techniques, because this is just playing within the color space using your images, and this is what we did. We wanted to detect the changes induced by an earthquake event, and that means we were not basically looking for two different spatial resolution images, but two different images, and in between these two images, when they were acquired, in between the earthquake has occurred. So if the almost the same technique, but little variation, that the pre-earthquake image was taken, post-earthquake image was taken from the same sensor, having time difference, and in between we are having an earthquake event. Now of course georeferencing has to be done, or image to image registration has to be done, so that both stacks together very nicely. Then I can do this technique on pen images, and I can also do this technique on list 3 images to detect changes induced by an earthquake. So I am having both the examples, where what we did, we assigned for in case of pen image, we assigned red channel to the post image, and for pre-earthquake scene, we assign green and blue. and then what it will bring, any changes which is in terms of reflection, that means reflection has increased, will appear in red color in this PCT, that is called pseudo color transformation or pseudo color transform image. Similarly, in case of list 3, pre-earthquake image was assigned red color. So, there is a difference here, and the pre-earthquake image was assigned here in case of PAN post color, because here we were handling the infrared channel, because we wanted to detect the moisture or water bodies. So, infrared channel was assigned red color in the pre image and post image green and blue, and by which we can again bring a pseudo color image and a transform image, and that will bring some beautiful results. So, let us see the example here. The same thing, it is a pre-earthquake image, post-earthquake image. Now, they have been blue, green, red, and 3 components, because this is additive color scheme was followed, and a new product has been created which is called pseudo color transform image. Now, results are like this, that on the left side you are saying pre-earthquake image of 26 March 99, here you are saying 31st March 99 earthquake, post-earthquake image, and earthquake occurred on 29th March, that means between these 2 dates. And so, this is something like matching 2 images or figures, which is not very convenient. So, using this pseudo color transformation technique, we created one single image which was showing the changes which has occurred between these 2 input images dates, and the red areas are showing the changes in terms of reflection, that increased reflection, and this is because of landslides which were induced by this Chamoli earthquake of March 29 of 99. So, then it becomes much easier, rather than interpreting these images having 2 different dates. Now, these 2 different dates images have been transformed using that color space concept, and a pseudo color transformation image was created, and this is what you see. Another important thing, you might observe that there are still white areas. White areas are depicting that no change between these 2 dates have occurred. That means there were already landslides here or here, which were not got disturbed, but other places it got disturbed. Now, these are digital images, so we can do further processing, like we can mask every other thing except the red area, like done on the right side image, and you can exactly match landslide affected area within that image. Similarly, one more example is here, pre-earthquake image, post-earthquake image of the same dates, same sensor, but when we merge it, it brings beautifully the new landslides or already enhancement into already existing landslides. So, white colors are again depicting that landslides were already existing, no change in terms of reflection, whereas red color are showing the changes, new surface has been exposed, means vegetation has disappeared, and that can happen due to landslides, fresh landslides, and that has happened because of that 29th March earthquake. Again, you can mask everything and you can bring only landslide affected region. You can do the measurements and other things very easily. Similarly, in many other earthquakes, same way we have did the color transformation. There we in the previous Chamoli example, we have taken PAN images, high spatial resolution images. Here we have taken the false color composite images, and still you can do the same pseudo color transformation as the rightmost image and depicts that one. If time gap is minimum, then you get the very good results. If time gap is large, you do not get those good results. One more example, and that is in playing with the infrared channel. Here we wanted to highlight that whatever has changes in terms of moisture or new water bodies because of an earthquake event, we wanted to highlight or bring out of these 2 input images. So, 2 input images, that is 4th March 2001, 4th January 2001, 29th January 2001, and in between on 26th of January 2001, Bhuj earthquake occurred. So, when we took these infrared channels and assigned the red color for pre and post green and blue, and when we made the pseudo color transform image, what you are seeing in this, that all red areas are showing the changes in terms of more moisture of water bodies. And a lot of because there is a co-seismic phenomena which is called liquefaction. So, in a large area north of epicentral area, and there were liquefaction occurred, and the water bodies for some time, or water on for the some time appeared on the surface and then disappeared. In between these data were acquired, and when we did the this pseudo color transform analysis, we get this thing very clearly. These images, as I was mentioning, that once you can understand the the magic or advantages or efficacies of color space, you can really exploit and create new products using high spatial resolution or high spectral resolution, two different sensors images of the same area, or even the same sensor images having two different dates of the same area. So, various ways you can really exploit this color space and can create new products. So, this brings to the end of part 2 of pre-processing of GIS database, and then we will go and discuss later. After this, we will discuss the last part, that is part 3. Thank you very much.